So again, welcome to Operating System CS332 class. In this lectures, we're going to cover chapter 9 of our course textbook, which is a Uniprocessor scheduling. So again, in a multi-program system, multiple processes exist concurrently in main memory. So each process alternates between using a processor and waiting for some event to occur, such as the compression of one I/O operation. Also, the processor or the processes are kept busy by executing one process while the others wait. So the key to multi-programming is scheduling. Again, scheduling the processes to execute tasks. So in fact, there are 4 types of scheduling that are typically involved in this, again, lectures. And we shall go through each of them. So our main objective first is we're going to discuss 4 types of scheduling, and the long-term, medium-term, short-term, and also I/O scheduling. Also traditional UNIX scheduling system, and also some few scheduling algorithms. So again, there are 4 types of schedulings that are typically involved. First, we have the long-term scheduling. Also, we have the medium-term scheduling, short-term scheduling, and also I/O scheduling. So again, one of these I/O scheduling is more conveniently addressed in chapter 11 of our course textbook. So in this chapter 11, we discuss about I/O systems. So in these lectures, we're going to discuss about the long-term scheduling, medium-term, and also the short-term. So this, again, lectures begin with examination of 3 types of process scheduling, showing how they are related. Also, we see that long-term scheduling and medium-term scheduling are driven primarily by performance concerning that is related to the degree of multi-programming. So these issues are dealt with to some extent in chapter 3 when we cover processes. And also more detail will be discussed. This was discussed in chapter 7 and 8. So the remainder of these lectures will concentrate on short-term scheduling and will be limited to the consideration of scheduling on a uniprocessor system. Then again, in our next chapter, which will be chapter 10, we'll discuss the multi-process system. Now, because of the use of multiple process has more additional complexity, it is best to focus on the uniprocessor first, so that difference among scheduling algorithms can be clearly seen. So again, these lectures will cover only the uniprocessor scheduling system. So a long-term schedule is again the decision to add to the pool of a process to be executed. Then a medium-term scheduling is the decision to add to the number of processes that are partially or fully in main memory. Short-term scheduling is the decision as to which a variable process will be executed by the processor. Then I/O scheduling, which we are going to cover around chapter 11 in I/O system, is the decision as to which process pending I/O request shall be handled by a variable I/O device. So process scheduling, here we say process schedule normally aim is to assign processes to be executed by the processor in a way that meets the system objectives, such as the response time, the throughput, and process efficiency. And we discussed this when we were in chapter 3 about processes. The main goal of an operating system is to make sure that we utilize, or the processes are utilized in an optimization form, must be always be busy. So here we're going to say the aim of a processor scheduling is to assign processes to be executed by the processor or processes over time in a way that meets the system objective, such as response time should be good, the throughput, and also the process efficiency. Process efficiency again means We want the process not to be idle, should be used as much as possible to optimize the usage of the processor. So again, the name suggests, here we are going to break down this concept into three separate functions. As we said, we have the long-term scheduling, medium-term scheduling, short-term scheduling. The IO schedule will be again in chapter 11 of the course textbook. So the figure below here relates to scheduling function to the process state transition. So scheduling again and process state transition. So for example, in the first diagram, we can see a process, a new, then comes to the ready suspend state. So we have from new to long-term scheduling, and long-term scheduling from ready suspend to ready, we can have medium-term scheduling. So from here again, the long-term schedule is performed when a new process is created. So you can see that. So this a new process is created, a long-term schedule again is performed. And also this is a decision whether to add a new process to the set of processes that are currently active. Now with the medium-term schedule, it's part of the swapping function. It's part of the swapping function. So this is a decision whether to add a process to those that are at least partially in main memory and therefore available for execution. But short-term scheduling is actual decision of which ready process to execute. So we can say from ready to running. So the whole concept is on this diagram. It shows in this graph. When a new process is created, again, a long-term schedule is performed. Then from ready or suspend state to ready state, we may have a medium-term scheduling. Then from ready to running, that's normally where again, short-term scheduling takes place. Also from block or suspend to block state, we may also have a medium-term scheduling. So we can see in this figure also, reorganizing the state transition diagram to suggest the nesting of a scheduling functions. So we can see the outer is the long term. In the long term, again, as we said, is when a new process is again created. Then we have the medium. In the medium section, we can see again block, suspend, or ready suspend. Then the short-term scheduling is running, ready, and block transition area. So again, scheduling normally affects the performance of a system because it determines which process will wait and which will progress. So this point of view is presented in this figure 9.3, which again shows that the queues involved in the state transition of a process. And fundamentally, scheduling again is a matter of managing queues to minimize queuing delay and also to optimize the performance in the queue environment. So we can see that the main goal here, so we have a diagram, we have the long-term scheduling, a new batch jobs, interactive users. Then we move to the ready queue. From ready queue processor, we have the short-term scheduling, etc. So we start with the long-term scheduler. So we say the long-term scheduler normally determines which programs are admitted to the system for processing. So again, long-term scheduler determines which programs are admitted to the system for processing. So it controls the degree of multi-programming. And also once admitted, a job or a user programs become a process and is added to the queue for the short-term scheduler. And also in some systems, a newly created process begins in a swap out condition in which case it is added to a queue for a medium-term scheduler. So in a batch system, or for the batch portion of a general purpose operating system, newly submitted jobs are routed to disk and added in a batch queue. So again, the long-term scheduler creates processes from the queue when it can. There are two decisions involved here. First, the scheduler must decide when the operating system can take on one or more additional process. And secondly, the scheduler must decide which job or jobs to accept and turn into processes. So again, the decision as to when to create a new process is generally driven by the desired degree of multi-programming. So the more processes that are created, the smaller is the percentage of time that each process can be executed. That is, again, the more processes are competing for the same amount of process time. So a long-term scheduler may limit the degree of multi-programming to provide a satisfactory service to the current set of processes. Also, each time a job terminates, the scheduler must decide to add one or more new jobs. Additionally, if the fraction of time that the processor is idle exceed certain threshold, then the long-term scheduler must be invoked. So again, the decision as to which job to admit next can be on a simple first come, first serve basis, or it can be a tool to manage system performance. Now, the criteria used may include the priority or expected execution time or the I/O requirements. So again, for example, if the information is available, then the scheduler may attempt to keep a mix of a processor bound or I/O bound processes. Also, the decision can depend on which I/O resources are to be requested in attempt to, again, balance the I/O usage. So for an interactive programs in a time sharing system, a process creation request can be generated by the act of user attempting to act or to connect to the system. Because time sharing users are not simply queued up and kept waiting until the system can accept them. Rather, the operating system will accept all the authorized comers until the system is saturated, using some predefined measure of saturations. So at that point, again, a connection request is met with a message indicating that the system is full and the user should try again later. So again, the long-term create a process from the queue when it can, and again, must be decided. When the operating system can take on one or more additional process, and also which jobs to accept and turn into process. The concept again use first come, first serve, or a priority, and also expected execution time I/O requirement. Now, with required to midterm scheduling. Midterm scheduling, again, is part of swapping function, as we mentioned earlier. And the issues involved are discussed again in our course textbook in chapter 3 when we cover the processes. Typically, the swapping in decision is based on the need to manage the degree of multi-programming. So on a system that does not use virtual memory, then the memory management is also an issue. So the swapping in decision will consider the memory requirements of the swap out process. In terms of, again, the short-term scheduling, which also known as the dispatcher, also known as dispatcher, execute more frequently than the short-term scheduler, again, execute more frequently. So in terms of frequency of execution, the long-term scheduler executes relatively infrequently. And again, makes coerced gain decision of whether or not to take on a new process and which one to take. So again, the long-term scheduler executes very, very infrequently. But in relate to the short-term memory, again, execute more frequently than the long-term memory. Also, the medium-term scheduler is executed somewhat more frequently to make a swapping decisions. But the short-term scheduler, also known as we said, the dispatcher, execute most frequently and makes the first grain decision on which process to execute next. So again, short-term scheduler is invoked whenever an event occurs that may lead to the blocking of the current process, or that may provide an opportunity to preempt a current running process in favor of another. So example of such event can be clock interrupt, IO interrupt, operating system calls, or signals. Example will be the semaphores. So again, the main objective of a short-term scheduling is to allocate processor time in such a way to optimize one or more aspects of system behavior. So the main goal is optimization of the system behavior. Generally, a set of criteria is established against which various scheduling policy may be evaluated. Now, the commonly used criteria can be categorized along two dimensions. First, we can make a distinction between user-oriented and also the system-oriented criteria. We have user-oriented criteria, system-oriented criteria. Now, with the user-oriented criteria related to behavior of the system as perceived by the individual user or process. So an example is a response time. An example is a response time in an interactive system. So a response time is the elapsed time between the submission of a request until the response begins to appear as output. Also, this quantity is visible to the user and is naturally of interest to the user. And we would like, again, a scheduling policy that provide good service to various users. Now, in the case of response time, the threshold may be defined, say 2 seconds. Then a goal of scheduling mechanism should be to maximize the number of users who experience an average response time of 2 seconds or less. So again, other criteria are system-oriented. So with the system-oriented, that's the focus is on the effective and also efficient utilization of the processor. The focus of system-oriented criteria focus on effective and efficient utilization of the processor. User-oriented criteria relate to the behavior of the system as perceived by individual user or the process. So an example is a throughput, which is, again, is the rate at which processes are completed. This is certainly a worthwhile measure of system performance and one that we would like to maximize. However, it focuses on the system performance rather than service provided to the user. So throughput is of concern to the system administrator, but not to the user population. Whereas the user-oriented criteria are important on virtually all systems, system-oriented criteria are generally of minor importance on single-user systems. So another dimension along which criteria can be classified is those that are performance-related and also those that are not directly performance-related. So here we have the short-term scheduling criteria in terms of performance. We talk about response time and the throughput as a good example. So the criteria can be classified into performance related, and with predictability, it will be non-performance related. With the performance related, we can have quantitative or can be easily measured. But performance, non-performance related will be qualitative and it's hard to measure. So criteria that are not performance related are either qualitative in nature and do not lead themselves readily to measurement and analysis. Very difficult again. So an example of such criterion would be predictability or predictability. We would like for a service provided to users to exhibit the same characteristics over time. Now, independent of other work being performed by the system, but to some extent, this criteria can be measured by calculating variances as a function of workload. However, this is not nearly as straightforward as measuring throughput or response time as a function. Now, the following table also summarizes the case scheduling criteria. And these are again interdependent, and it is impossible to optimize all of them simultaneously. For example, providing a good response time may require scheduling algorithm that switches between processes frequently. But this increases the overhead of the system and also reducing the throughput. So that's again, the design of the scheduling policy involve compromising among competing requirements, also relative weights given the various requirements would depend on the nature and also the intended use of the system. And in most interactive operating systems, whether a single user or timeshare, adequate response time is the critical requirement. And because of the importance of this requirement, and because the definition of adequacy will vary from one application to another, this topic again will maybe explored in our future lectures about optimization of operating systems. So we have the throughput of processor utilization time, the fairness, enforcing priorities, and these are all again scheduling criteria. So again, in many systems, each process is assigned a priority. And again, the scheduler will always choose a process of higher priority over the one with lower priority. So the diagram here again shows the use of priorities. The queue diagram is simplified, ignoring the existence of multiple block queues and also of suspended states. Instead of single ready queue, we provide a set of queues in descending order of priority. So we have RQO, RQ1, RQ, and this is again based on the priorities. So when a scheduling selection is to be made, the scheduler will start at the highest priority ready queue, which is RQ0. And then if there are one or more processes in the queue, a process is selected using some scheduling policy. So if RQ0 is empty, then RQ1 will examine and so on. So one problem with the pure priority scheduling scheme is that the lower priority process may suffer starvation. Now, when we talk about starvation, we mean that the ones with the lower priority may stay in the queue for long, may not get a chance of using the processor in time. So if this behavior, again, the starvation is not desirable, then the priority of the process can change with its age or execution history. Again, we will give one example of this in the lecture slides coming soon. So the table here again presents some of the summary information about various scheduling policies that are examined in this section or in these lectures. So we can see different types of first come, first serve, round robin, SPN, again, then the scheduling functions, decision mode, throughput, response time, overhead, effect on process, and also starvation. Now with the first algorithm, first come, first serve, we can see that starvation is no, but overhead also is very good, it's minimal. But with SPN, overhead can be high. With SRT, overhead also can be high, and the rest. In terms of throughput, the first come, first serve is not emphasized. But with the round robin, it may be low if quantum is too small. So these are all the comparison of all the algorithm, and we shall go through each of them. So first, the selection function. And the selection function normally will determine which process among the ready processes is selected next for execution. So the function may be based on priorities, resource requirements, or the execution characteristics of the process. And also there are three quantities that are very significant. We have W, that's the time spent in system so far, that's the waiting. And also E will be the time spent in execution so far. And S will be, again, the total service time required by the process, including the E. Generally, this quantity, again, must be estimated or supplied by the user. Estimated or supplied by the user. Then the decision mode will specify the instance in time at which the selection function is exercised. Specify the instance in time at which the selection function is exercised. And we have two general categories, the non-preemptive and also the preemptive. And we start with the non-preemptive versus preemptive. So with the non-preemptive, we say in this case, once a process is in the running state, it contains or it continues to execute until it terminates, or it blocks itself to wait for IO or to request some IO service. So again, with the non-preemptive, once a process is in a running state, it will continue until it terminates or block itself for IO or to request some IO service. Now with the preemptive, the currently running process may be interrupted and move to the ready state by the operating system. So the decision to preempt may be performed when a new process arrives, or when an interrupt occurs that places a block process in the ready state, or periodically based on a clock interrupt. So as we describe the various scheduling policies, we will use the set of processes in previous table as a running example. So here we can think of this as a batch jobs, with the service time being the total execution time required. Alternatively, we can consider this to be ongoing process that require alternate use of the processor and IO in a repetitive function. In this latter case, the service times represent the processor time, which require in one cycle. In either case, in terms of queuing model, this quantity corresponds again to the service time. So we may have a process, the arrival time, and also the service time. So this may be a process scheduling, A arrival time 0, the service time is 3, and B 2 and 6, and etc. So we will start with the first come, first serve algorithm. So here the simplest scheduling policy or algorithm is again the first come, first serve. Also known as again first in, first out, kind of a concept in data structure, queue data structure, first in, first out, or queue scheme. Now here as each process becomes ready, it simply joins the ready queue. Now, when the current running process ceases to execute, then the process that has been in the ready queue the longest is selected for running. So that's why it's first come, first serve. So again, when the running process ceases to execute or completed, then the next process that has been in the queue for long will be executed. So again, the first serve or first come, first serve performs much better for long process than short ones. Also, another difficulty with the FCFS is that it tends to favor processor-bound processes over the IO-bound processes. So consider that there's a collection of processes, one of which mostly use the processor or the processor bound, and the number of which favor IO bound. When a process bound process is running, all of the IO bound process must wait. Some of these may be in the IO queues, which will be in the block state, but may move back to the ready queue while the processor bound process is executing. At this time, most or all of the IO devices may be idle, even though there is potentially work for them to do. Now, when the current running process leaves the running state, then the ready IO bound process quickly moves through the running state and become blocked on the IO events. So if the processor bound process is also blocked, the processor becomes idle. So first come, first serve may result in inefficient use of both the processor and the IO devices. So again, first come, first serve is not an attractive alternative on its own for a uniprocessor system. However, it is often combined with a priority scheme to provide an effective scheduler. So the scheduler may maintain a number of queues, one for each priority level, and dispatch within each queue on first come, first serve basis. We see one example of such system later in our discussion of feedback scheduling. So the next one is the round robin. And with the round robin, again, this is a straightforward way to reduce the penalty that short jobs suffer with first come, first serve. Is to use again preemption based on a clock. And the simplest search policy is again the round robin. So a clock interrupt is generated at periodic intervals. Now, when the interrupt occurs, the currently running process is placed in the ready queue. And the next ready job is selected on a first come, first serve basis. And again, this technique is also known as time slicing. So also known as time slicing because each process is given a slice of time before being again preempted. So with the round robin, the principal design issue is the length of the time quantum or slice to be used. Now, if the quantum is very short, then the short processes will move through the system relatively quickly. On the other hand, there's a processing overhead involved in handling the clock interrupt. and also performing the scheduling and dispatching function. That will be one of the drawback. So a very short term or a very short time quanta should be avoided. So round robin is particularly effective in general purpose time sharing system or a transaction processing system. So the drawback, one of the drawback for round robin is its relative treatment of processor bound and IO bound process. So one useful guide is that the time quantum should be slightly greater than the time required for the typical interaction or process function. So we have a process allocated time quantum, then interaction completed, then we can see the response time, the short term Q again minus X quantum, and also response time. So again, one useful guide based on these diagrams here is that the time quantum should be slightly greater than the time required for a typical interaction or process function. And if it is less, then most processes will require at least 2 time quantum. The diagram here again shows the effect this has on response time. And we should note that again, limiting time or the limited case of a time quantum that is longer than the longest running process, the round robin degenerate to again first come, first serve basis. So again, we're going to suggest a refinement to round robin that is referred to as again a virtual round robin. So here we have a diagram concept, queuing diagram for again virtual round robin scheduling. And the diagram here shows the scheme. New process arrive. New process arrive and join the ready queue, which is managed on the first come first serve basis. Now, when a running process times out, it's returned to the ready queue. And then when the process is blocked for IO, it joins the IO queue. And then so far, this is as usual. Now, the new feature is an first come first serve auxiliary queue. We have the first come first serve auxiliary queue in which processes are moved after being released from an IO block. Now, when a dispatching decision is to be made, processes in the auxiliary queue get preference over those in the main ready queue. Then when a process is dispatched from the auxiliary queue, it runs no longer than the time equal to the basic time quantum minus the total time spent running since it was last selected from the main ready queue. So again, performance studies by the researchers indicate that this approach is indeed more superior to round robin in terms of fairness, according to our textbook also. We also have, again, the shortest process nest, which is the SPN. So another approach is to reduce the bias in form of long process inherit in first come, first serve. Again, the goal here is to reduce the bias or the errors in favor of long process inherit in first come, first serve. And this is the shortest process nest policy. So this is again non-preemptive policy in which the process with the shortest expected processing time is selected next. So the short-term process will jump to the head of the queue past the longer jobs. So again, the diagram shows the result for an example. We should know that the process E service much earlier than first come, first serve. Now, the whole thing overall performance is also significantly improved in terms of response time. However, the variability of response time is increased, especially for the longer processes. And also this make the predictability to be reduced. So one difficulty with the SPM policy is the need to know or at least estimate the required process time of each process. So for batch jobs, the system may require the programmer to estimate the value and also supply it to the operating system. Then in a production environment, the same job runs frequently and the statistics may be gathered. For interactive process, the operating system may keep a running stage of each burst for each process. So again, a risk with SPN is the possibility of starvation also, a starvation for longer process, as long as there's a steady supply of shorter processes. On the other hand, although SPN reduces the bias or errors in favor of longer jobs, and it is still not a desirable for time sharing and transition or transaction processing environment because of the lack of preemption. So this will lead us to the concept of shortest remaining time. Again, the size of the coefficient as a function of its position in expansion is shown in the previous figure. So here we say the larger the value of, the greater is the weight given to a more recent observations. Now the shortest remaining time, which is the SRT policy, is also a preemptive version of SPN. In this case, the scheduler always chooses the process that has the shortest expected remaining process time. When a new process joins the ready queue, it may in fact have a shorter remaining time than the currently running process. Accordingly, the scheduler may preempt the current process when a new process becomes ready. But as with SPN, the scheduler must have an estimate of processing time to perform selection function. And there will be a risk of starvation also of the longer process. So SRT does not have the bias in favor of long process found in FCFS also. And unlike the round robin, an additional interrupt are generated, reducing the overhead. And he also, we say, should give a superior turnaround time performance to SPN because, as we said, the short job is giving immediate preference to the running longer job. So again, SRT should also give a superior turnaround time performance to SPN. The next one is the highest response ratio, NES, which is HRRN. So here we say choose NES process with the greatest ratio. So again, as with the SRT and SPN, the expected time must be estimated in order to use the highest response time next. So while the shorter jobs are favored, aging without service increase the ratio so that the longer process will eventually get past competing the shorter again jobs. So the ratio will be again time spent waiting plus expected service time divided by expected service time. So if we have no indication of relative length of various process, then none of the SPN, SRT, and HRRN can be used. So again, another way of establishing a preference for shorter jobs is to penalize jobs that have been running longer. In other words, if we cannot focus on the time remaining to execute, let us focus on the time spent in execution so far. So this way, again, to do this is follows. Scheduling is done on, again, preemptive at a time quantum basis, and also dynamic and priority mechanism is used. So when a process first enters the system, it places in RQO, as we saw in our previous diagram, and after its first preemption, when it returns to the ready state, it is placed in RQ1, and we keep going. So we also have what we call the fair share scheduling. So again, first thing we should know, a shorter process will complete quickly without migrating very far down the hierarchy of ready queues, but a longer process will gradually drift downward. So the shorter process are favored over older, longer process. And again, this approach is known as the multi-level feedback, meaning that operating system will allocate a processor to a process, and when the process blocks or is preempted, it feeds it back into one of the several, again, priority queues. So all the schedule algorithm discussed so far treat the collection of ready process as a single pool of process from which to select the next running process. So this pool may be broken down by priority, but is otherwise homogeneous. However, in a multi-user system, if individual user application or jobs may be organized as multi-level process or threads, then there's a structure to the collection of process that is not recognized by the traditional scheduler. So again, from the user's point of view, the concern is not how a particular process performs, but rather how his or her set of process, which constitute a single application, performs. So a fair sharing scheduling, here we say the scheduling decision based on the process set, and also each user is assigned a share of the processor. Now the objective is to monitor usage to view fewer resources to users who have had more than their fair share, and more to those who have had less than their fair share. So a fair share scheduler, the following formula apply to the process J in a group K. So we have process J, here we say the CPU I minus 1/2, and we make sure we share among the whole concept, a fair share scheduler. And we also have the traditional UNIX scheduling. Normally it's based on SVR3 and also 4.3 BSD units. Here we say these systems are primarily targeted at a time sharing interactive environment, also designed to provide good response time for interactive users while ensuring that low priority background jobs do not starve. And also employ multi-level feedback using round robin within each of the priority. Also make use of 1 second preemption. And also the priorities based on process time and also execution history. And this is our scheduling formula. So again, before we end, we should also know that the term fair share indicate the philosophy behind such as a scheduler. So each user is assigned a weighting of some sort that defines the user share of a system resources as a fraction of the total usage of those resources. So each user is assigned a share of the processor. So this will be, again, the conclusion of our lectures. And again, wish everybody the best. And our next lecture will focus on chapter 10, which is also, again, a scheduler system, for this time a multi-processor system. So again, wish everybody the best and thank you for your time.